All right. Uh, at the end of the last class, we had just, I think, unlocked the secrets of the universe. So we saw how we could use molecular orbitals to predict a chemical reaction and understand exactly what's going to happen. Uh, and it was all based on identifying the donor orbital and the acceptor orbital. So the donor orbital should be a filled orbital. So number one, to be a donor, you have to have electrons. If you don't have electrons, you can't donate electrons. So it must be a filled orbital. Say that's the first thing. Must be relatively high in energy. The higher energy it has, the more likely it is to go out and attack other orbitals. We use this language of attack when we talk about an orbital donating to another one. We would say this pair of electrons attacks this atom. All right, so what type of orbital would be most likely to be a high energy filled orbital? A non-bonding orbital, a lone pair, right? So lone pair. And then what would be second best? Let's say we have a molecule that doesn't have any lone pairs in it. What would be the second best donor orbital? A pi bond, yep. And what are going to be the worst donor orbitals? Sigma bonding. What about electronegativity? What kind of electronegativity would make something a better donor? So we're looking for something that makes it high in energy. That means low electronegativity. And then what about formal charge? What kind of formal charge will make something more likely to donate electrons? Negative. Negative formal charge makes something a great donor, right? It's got extra electrons to donate. Neutral is okay. And positive would make it a terrible donor. All right, so the question is, when I considered type of orbital, I didn't consider antibonding orbitals. Why didn't I do that? Well, simple reason, they're not filled. So we didn't consider antibonding orbitals because generally they don't have electrons in them. So they can't act as donors. So the question is, if an antibonding orbital were filled, it would be a good donor. Yes, but we will never actually, in this course, have any electrons in antibonding orbitals. All right, so the best kind of donor orbitals, the examples we said would be lone pairs, particularly lone pairs on low electronegativity atoms. So one of the best would be on the cyanide ion. Cyanide, you have a lone pair on nitrogen. and you have a lone pair on carbon, which one of those is going to be the best donor in that molecule? The one on carbon. Yeah, so this sometimes we'll represent it with like a little bubble to represent the orbital and then put the two arrows in it to represent the two electrons. Sometimes we'll leave those out, but this would be a non-bonding on carbon. That would be a great donor orbital. You could also have lone pairs on other atoms. Lone pair on sulfur would be a great donor because it's not particularly electronegative. So if you had, say, that molecule, these lone pairs on sulfur would be great donors. You start to get lone pairs on more electronegative atoms, well, they're not going to be quite as good donors. They're still good donors, but not quite as good. So water's got two donor orbitals, two lone pairs. Those are pretty good donors. And then we said, you know, our next level, once we get past lone pairs, our next level of potential donors would be things like pi CC. Pi CC is a pretty good donor. It does look like a burger, yeah. So that would be in this molecule, C2H4. Pi CC would be, oops, bottom half of my C didn't show up. Pi CC. That's a decent donor. It turns out that other pi orbitals, when you have an electronegative atom, that usually drags the energy down enough to where they're not particularly good donors. So, as an aside, so if you had a molecule like this, pi CO would not be particularly good. So the question is, what is considered really electronegative? And I don't have a line for you. So, you know, we talk about these general principles, like we did on the last slide. These are the general things to look for. And now I'm just giving you some specifics. And there's not really a line, like, are there some cases where pi CO might be a donor? Yes, but it's going to be less likely. So I'm trying to point out the most likely scenario, most of the time, your donor is going to be a lone pair. And if there's no lone pair, then it's probably going to be pi CC. And if there's neither one of those things, then that molecule probably won't act as a donor. So, basically the rest of the course really gets into specific reactions that do and don't happen. And so then you start to build in your mind that terrain of, okay, these are the good donors and these are the not good donors. And so, part of that just comes from experience. But you'd be unlikely to see pi CO act as a donor. Not to say it never will, but it usually won't. And part of the reason for that is pretty clear. When I have a molecule that has a pi CO orbital, what other orbital that's a better donor does it also have? It has oxygen lone pairs. So if this molecule were going to act as a donor, it would be those oxygen lone pairs that would act as donors instead. So part of it just has to do with when you have a pi CO orbital, there's a better donor orbital right there in the same molecule. Whereas when you have a carbon-carbon pi bond, you can have molecules that don't have any better donors than that pi bond. All right, so those are some examples of donor orbitals. What about what makes a good acceptor orbital? Well, we said it last time. What kind of energy are we looking for acceptors to have? Relatively low energy. And I'll add in, again, this has to be, must be empty, so that precludes any bonding orbitals or lone pairs. The lower energy it is, the better acceptor it is. So what would the lowest energy type of empty orbital we could have be? Well, sigma would be the lowest energy orbital we could have, but it will always be filled because it's a bonding orbital. All right. This goes back to the little trick that I pointed out. Sometimes you have these vacant non-bonding orbitals. When you have one of those vacant non-bonding orbitals, that's going to be the best possible acceptor. Remember when we went back, we said we broke down our MO diagrams into sigma, pi, non-bonding, pi star, and sigma star. Bonding are always filled, anti-bonding are always empty. Non-bonding, usually they're filled, usually they're lone pairs, but sometimes you have those vacant non-bonding orbitals. And so if you do, that's going to be the best possible acceptor. So when we think about the best kind of acceptor here, vacant non-bonding would be the best. So we said that would be something you have when you have a carbocation. But that's fairly rare. So then what would be second best? Pi star, yep. So pi star, particularly when there's an electronegative atom. Well, I'll talk about electronegativity next, so I guess I'll just say pi star is good. And then sigma star is okay. In terms of electronegativity, what's going to make an orbital have low energy? High electronegativity, yep. Ooh. And then in terms of formal charge, what kind of formal charge is going to make the orbital lower energy? Positive. So positive formal charge is great. Neutral is fine. Negative formal charge is terrible. If you think about it, if something has a negative formal charge, you wouldn't ask it to take on more electrons. So it wouldn't be happy about that. So then, examples of our best acceptor orbitals, like we said, carbocations, if you have a carbocation, its geometry looks like this, and it's got this wide open empty p orbital just screaming for electrons. Another really good acceptor would be pi star Cx, where X is electronegative. So for example, if you had formaldehyde, the pi star C orbital would be an outstanding acceptor. Which side, carbon or oxygen, is going to have a bigger part of the antibonding orbital? Let's go back a bit. Let's see, where did we talk about it? So back when we talked about CCl, we said the more electron density goes next to the more electronegative atom. So the bonding orbital lies more on the more electronegative atom, but the antibonding orbital has its bigger part on the less electronegative atom. So coming back to this example, my pi star CO is going to have a big part on the carbon and a small part on the oxygen. And then sigma star Cx, where X is an electronegative atom, also tends to be a pretty good acceptor. So, really common acceptor that I like to use because it rhymes when you say it. What would the acceptor orbital on that molecule be? Sigma star CBr. Yeah. Sigma star CBr. So that also is a very good acceptor orbital. So the question is, if bromine has the small lobe, wouldn't carbon be the one accepting the electrons? And the answer is yes. So we saw in this example, with sigma star CCl being our acceptor, we donated to the carbon. So yeah, we generally donate to the less electronegative atom. Now, as an aside here as well, it turns out that pi star CC, even though based on our general rules seems like it might be a pretty good acceptor, turns out it's not. So the question is, all right, how do we notate which atom is actually going to accept the electrons? Generally, you notate that with the curved arrows. So here, in this example, we said we're donating from the non-bonding on sulfur we're donating into sigma star CCl. By saying that, it's not clear whether sulfur is going to bond to the carbon or sulfur is going to bond to the chlorine, but when we draw the arrows, we make sure the arrow goes from the sulfur lone pair to the carbon, and that makes it clear which end is actually accepting the electrons. One mistake people sometimes make is to draw the arrow going to the bond because they think, oh, I'm attacking the CCl bond, so I'm going to draw the arrow there. You don't want that to happen. You want your arrow to go to the atom that's actually going to accept the electrons. So the question... So the question is it usually a single atom that breaks off? And the answer is not necessarily. We'll see examples where a whole group breaks off. But it'll always be the more electronegative atom that breaks off. We generally attack the less electronegative atom and not the more electronegative atom. So these are your go-to donors would be lone pairs and pi CC, and your go-to acceptors would be non-bonding orbitals that are empty, pi star CX or sigma star CX. Those are going to be your most common donors and acceptors. The language that's often used here, and so I think it's important to introduce the language. The highest occupied molecular orbital, so whatever molecular orbital is highest in energy in the molecule, we call the HOMO, and that's going to be the most likely donor. It's not the only possible donor in a molecule, but it's the most likely one. And then the most likely acceptor would be what we call the LUMO, the lowest unoccupied molecular orbital. So when you draw an MO diagram, you can always go and identify, all right, where's my highest energy filled orbital, call that the HOMO, and you can identify where's my lowest energy empty orbital and call that the LUMO. Collectively, these are called the frontier molecular orbitals. Frontier because they're the ones that are kind of on the edge of being filled or unfilled. So going back to some of the MOs we've drawn, to some of the MO diagrams, I'll come back here in a second. But going back here where we said in this case, the sulfur lone pairs were the best donor. We would say that's the HOMO. And sigma star CCl, that best acceptor, that was the LUMO in that molecule. I usually stick with the terms donor and acceptor because in some reactions, the donor may not be the actual highest energy one in the molecule in your MO diagram. But you'll definitely see sources that just refer to HOMO and LUMO all the time. We'll usually talk about donor and acceptor. Because there can also be multiple donors and multiple acceptors in a reaction, whereas there can only be one highest occupied molecular orbital or one lowest unoccupied. All right, so here's 3 examples. Relatively quickly, without drawing a full MO diagram, I want you to try and identify the HOMO and the LUMO in each of these 3 molecules. All right, first molecule here, propyl bromide. What do we have for the HOMO? Bromine lone pair is the HOMO, the LUMO, sigma star CBr. All right. Second molecule. What's the HOMO? Lone pairs on oxygen, yeah. And the LUMO? Pi star CO. And then this last one. HOMO is going to be pi CC. There's no lone pairs. And the LUMO? Pi star CC. Yeah, so we practice a little bit drawing those full MO diagrams, but in the end, the key is being able to look at a molecule and identify, all right, where are my possible donors, where are my possible acceptors? And being able to identify the HOMO and the LUMO relatively quickly will help us do that. What questions do you have? Okay. So sometimes you'll have molecules that have multiple possible donors and multiple possible acceptors. So slightly more complicated molecules. So take a look at these 2 molecules. In each one, try and identify, all right, what are my pretty good donors, what are my pretty good acceptors in that molecule, and the same for the one on the right. All right, so what do we think would be potential donors in the left-hand molecule? NO. Oh, non-bonding on oxygen. Yep. So the oxygen lone pairs. Pi CC. Yeah. Those would be probably the only 2 I would expect to potentially act as donors. What about acceptors? Pi star CO would be my best one. Pi star CC, probably not. I'll put it in brackets. It would be the second best one there, but all right, how about the one on the right? All right, lone pair on oxygen, lone pair on nitrogen. Pi CN, probably not. That's one of those that I said those kinds of orbitals don't often, where you have an electronegative atom like nitrogen, they don't often act as donors. But and then acceptors, pi star CN, sigma star CO. Yep. Turns out a sigma star CO there is a pretty decent acceptor as well. All right, so when you look at molecules now, and when you see functional groups you're familiar with, hopefully what's going to happen is you're going to start to recognize, oh, this functional group seems like it might be a pretty good donor. This functional group seems like it's often going to be a good acceptor. And so you can start to link those things together. All right, so I have a lot of words on this slide. So before you just start copying, let me talk for a minute about it. Curved arrows show electron donation from one molecule to another molecule or from one atom to another atom. They always start at the donor orbital. Remember, a curved arrow should always start at a pair of electrons. So I've mentioned this before. Your curved arrow should always start at a bond or a lone pair. And if it starts at a lone pair, you should draw in the lone pair. So remember to draw in the lone pair if that's where the arrow starts. So an arrow always starts at the donor orbital. And the curved arrow should always end at the atom that has the bigger lobe of the acceptor orbital. Remember, an acceptor orbital often has two atoms involved. An acceptor might be sigma star CBr or pi star CO. There's two atoms involved. The arrow is always going to end at one of them, and it's generally going to end at the one with the bigger lobe of the acceptor. And the bigger lobe of the acceptor orbital generally means the less electronegative atom. So whenever you have a donor and an acceptor, there will be a new bond formed between those two atoms. Every time there's a donor-acceptor pair, there'll be a new bond there in the products that was not there in the reactants. So going back to the example we did, we were donating from the sulfur lone pair to sigma star CCl. We formed a new bond between the sulfur and the chlorine and the carbon. And in addition, because we were donating into sigma star CCl, what had to happen to the CCl bond? It had to break. So because we're donating to sigma star CCl, that bond had to break. That'll be true in general. If the acceptor is an antibonding orbital, then you have to break that corresponding bond. All right, this last point down here, I want to illustrate because it doesn't necessarily make that much sense in the abstract. Occasionally, you'll have a curved arrow that looks like this. Occasionally, you have a bond that just breaks on its own. It's not something that happens all that frequently, but occasionally you have a bond that breaks on its own. So when you have a curved arrow like this, it only breaks a bond, does not form a new bond. There is no donor-acceptor interaction going on there. Question? So the question is this what happens in all decomposition reactions? And the answer is no. No. This specifically happens in a reaction called the SN1 reaction, which I would talk about in module like 15, 16. But it's kind of this rare occurrence because bonds don't want to break. So a bond just breaking on its own like this is not going to be something that happens a lot. But you will see examples where you have a curved arrow that doesn't have an associated donor-acceptor interaction. The common error here, what people commonly do, is they'll say, oh, this is the sigma CBr orbital donating to a bromine lone pair. Right? This is the most common error I'll see on the skill checkers. And, you know, in the tests in my summer school course. People will say sigma CBr donates to a non-bonding orbital on bromine. What's your first clue that that's an incorrect assumption? That's an incorrect explanation of what's going on. To be an acceptor orbital, what kind of orbital do you need to be? Empty. Is a bromine lone pair empty? No. So, you know, the first tip-off that this is a mistake is that this is not an empty orbital. What people are describing when they say this, they're really describing the transition that occurs. The sigma CBr orbital in this reaction step actually becomes a lone pair on bromine. That is a true statement. You know, it is accurate to say the sigma CBr orbital becomes a lone pair on bromine. But when we're thinking about donor-acceptor interactions, we're not talking about what happens to the orbitals in the products. We're only looking for the existing orbitals in the reactants. We're not talking about what they become in the products. So it's true that sigma CBr becomes a lone pair on bromine. But that's not a donor-acceptor pair. So I don't want you to get into this, to get into the trap of thinking every curved arrow has a donor-acceptor interaction associated with it. And yes, I'll go back a slide in a moment. All right, so this last point, just to reiterate, only curved arrows that form new bonds involve donor-acceptor interactions. So all that's left for us now is to do another example or two. So the student asked a question, when a skill builder talks about cartoon drawings of orbitals, the cartoon drawings of orbitals would be like these drawings that I made here. Yeah, the drawings that show the lobes of the orbitals. Yep. All right. That'll be it for today.